Hello everyone and welcome back to the third video in this series in which we've been going through the Step 1 paper from 2018, question by question, and just solving the questions in front of the camera. So, today we're going to be going through question 3, which I've written out here, so let's have a look at it. We've got 2 points, coordinates minus a0 and 2a0, where a is some positive constant, and then we've got a general point P, coordinates x, y, where y is positive and x is less than 2a. Okay, and then we're given these two angles, alpha and beta here. So straight away, it's quite clear how we should start this question, and that's by drawing a diagram. And if we look at the two actual parts of the question that we have to solve, part 1 and part 2, it seems to still be about the same thing. We've still got these angles beta and alpha, we've still got this point P, and we've got a curve. So it seems that it would be good for us to draw a diagram that will serve us well for the whole question. So for that reason, I'm just going to start by putting some time into drawing an accurate and quite large diagram. So let's do that. We've got our x axis and our y axis. We've got 0. We've got a point. We're told that a is positive, so we can put our point R here. Let's label that R minus a0. Okay, and then we've got our point S, which is going to be, let's say this is A, so we've got 2a0 here, that's S. And then we've got a general point P, where its y coordinate is positive and its x coordinate is less than 2a, so it's somewhere over here. Let's put it, I don't know, here. General point P, x, y. And then we're given a couple of angles. We're told that PRS equals alpha. So that's PRS. This angle here is alpha. Okay, and we're told that PSR is beta. So let's draw that on as well. Okay. And now we have to show that if this angle is twice this angle, then P must lie on this curve. So let's have a think about that curve. Y squared equals 3 lots of x squared minus a squared. So, because we've got a y squared here, this is going to be some kind of parabola. If we imagine taking square roots, we'd get a plus minus. So we're actually going to have symmetry along this axis. We're going to have two parabolic curves. And if we imagine where this is going to hit the x-axis, where y equals 0, that's going to be when this is 0. And that is exactly when x is either plus a or minus a. So we're actually going to hit here and here. Okay. And furthermore, if we imagine making x very, very large, so that it sort of dwarfs a, then we're going to have roughly that y squared is 3x squared. Or in other words, y gets closer and closer to the line root 3x. Or in fact, root 3x, but also minus root 3x. So we're going to be going off into these diagonals in all four corners. So, drawing that in, I think we're going to have a curve that looks a bit like this on the left. And then on the right, similarly, let's make it hit P. Cut the x-axis at plus a, and we're going to look like that. Okay, so we're trying to show that when twice this angle is equal to this angle, then P must be somewhere on this curve. So let's have a go at that. But actually, okay, so if we draw a line from P to actually hit the x-axis perpendicularly, that could be useful because then we actually know some of the lengths of these two right-angled triangles. Always helpful to draw a right-angled triangle when you can. So, because this is minus a0 and this is x0, then this length must actually be a plus x. Okay, so that's good. And then this height is just y because it's going up to this P P point. And then here we've got from 0 to x. So then from x to 2a, that length is just going to be 2a minus x. So now actually we've got two right triangles and we know all of the lengths apart from the hypotenuse. When we don't know the hypotenuse, we're going to use tan, aren't we? So that, it seems to be a good way in. So let's start some algebra. We're told that beta equals 2 alpha. Okay, and we know that if we look at tan alpha, what's that going to be? Opposite over adjacent. That's y over a plus x. And how about tan beta? Well, again, opposite over adjacent. That's y, and this time over 2a minus x. Okay, this is promising because we're trying to find that if beta equals 2 alpha, we're trying to find an equation in terms of y, x, and a. And here we've got tan alpha and tan beta in terms of these three variables. So let's see, let's use this condition beta equals 2 alpha. So beta equals 2 alpha, that implies that, well, let's incorporate our tans in. That means that tan beta is tan 2 alpha. Okay, and now what is tan of 2 alpha? We can use our double angle formulae. So that's just 2 tan alpha over 1 minus tan squared alpha. Okay, and you should really know that if you're going into step, but if you're unsure why that's true, and it's quite easy to derive from the definition of tan x as sine x over cos x, and then the double angle formulae for sine and cos, which you definitely should know going into step. So sine 2x is 2 sine x cos x, and cos 2x can be expressed a number of different ways, but I think the useful one for proving this result is actually that cos 2x is cos squared x minus sine squared x. Okay, so try and use these three simple expressions to prove that tan 2 alpha is 2 tan alpha over 1 minus tan squared alpha. But I'll leave that for you to do. But now, let's just multiply up by 1 minus tan squared alpha, just so that it's going to be a bit easier when we sub things in. At least I think it will be. Now, we've got an equation with tan beta and tan alpha. So, we can simply plug in our expressions for tan alpha and tan beta in terms of y, a, and x. And that should give us exactly what we want. Okay? So let's do that. Tan beta, so that's y over 2a minus x. 1 minus tan squared alpha, so that's 1 minus, and then squaring that, so y squared over a plus x squared, close brackets, equals 2 tan alpha, so 2y over a plus x. Okay, now, every term has a y in it. I'm going to divide through by y, and I'll just put in brackets, y is not equal to 0, because we know that from here. And I'm also going to times up by 2a minus x, and I'm going to times up by a plus x squared. And I think that should give me, this is going to become a plus x squared. This is going to become minus y squared. And then I'm going to get equals, well, I keep the 2, get rid of the y. This comes up, I get another a plus x, and then I also get a 2a minus x. Okay, and there's some algebra to do here, but I'll try and do it in as few steps as possible. So we want y squared equals, so I'll put y squared equals, so that's putting that over there, and then swapping the sides. What am I left with? I'm going to be left with a common a plus x, and then I'm going to get an a plus, another a plus x from here, and then I'm just going to get minus 2 lots of 2a minus x. Okay, so that's going to be minus 4a and then plus 2x. Don't worry about taking extra steps here if you need to. I'm just trying to save some room. And then from here, if we look at this, this gives us 3x minus 3a. Bring the 3 out, and we get a plus x times by x minus a. And then that just gives us, by the difference of 2 squared, 3 lots of x squared minus a squared. And that is as required, because that's what we're trying to show. So if beta equals 2 alpha, then P, the point P with coordinates x, y, satisfies this equation, which is exactly what we're trying to show. Okay, brilliant. So let's look at part 2. Part 2 says, find the possible relationships between alpha and beta when alpha is between 0 and pi, and P lies on this curve. And my first thought is, well, haven't we just shown the exact opposite of that? Haven't we? We've just shown that when beta equals 2 alpha, then y squared equals 3x squared minus a squared. And now they're asking us to say, okay, well, let's say y squared equals 3x squared minus a squared. What can we say about beta and alpha? So, yeah, we might think that actually we can just reverse all of these steps and show that when this is true, then beta equals 2 alpha. But I think the problem is that in the case that we just looked at, if we look back at our diagram, that's going to be when we're on this line. But in the question it says find the possible relationships. So probably what's going to happen is we're going to get beta equals 2 alpha out for this, but then we're going to get a different result here. Okay, so let's just try and run our argument backwards and see, I'll put this at the bottom actually, and see where it goes wrong. So let's look at our work. What steps can we reverse? I think all of these algebra steps are fine. We can reverse these. We can run the argument backwards and say if y squared equals this, then trying to work our way towards an expression for beta and alpha. All of these are reversible for sure. But the problem I think comes when, okay, tan beta equals tan 2 alpha, does that imply that beta equals 2 alpha? And it doesn't actually, because, I'll just demonstrate this quickly. Remember when you draw tan x, it's actually multi-valued. So between pi and minus pi, it's nice and single valued, isn't it? It looks like this. But beyond this principal branch of tan, we get some more branches. And so actually, you could have, for example here, 2 different values of x which share the same value of tan x. Okay, because they're the same height but different x coordinates. So that actually means that we can't just say that tan beta equals tan 2 alpha automatically implies beta equals 2 alpha. In fact, the condition we need for this implication to work, for us to be able to go this, therefore this, is that we need to be in this region here. We need to be in between minus pi and pi. So that gives us a bit of a clue as to what the question is asking. So let's try and write it out. Okay, so new sheet of paper. Let's have a go at part 2. There we go. So part 2. Let's say from part 1, we have that when y squared equals 3 lots of x squared minus a squared, tan beta equals tan 2 alpha. Okay? And let's say this implies that beta equals 2 alpha when, look at, just remembering our tan diagram, that's when beta and 2 alpha are in the region minus pi and pi. Okay? But let's quickly remember, actually, y is greater than 0 here, and x is less than 2a. Okay, so just quickly looking back at our diagram, we're looking at this part, so sort of here, all the way up to 2a. Let's just draw this up to here. And then we're also looking at this branch as well. But the thing is, if we look at alpha here, we're told that alpha is between 0 and pi. So actually, we know that alpha is positive, and we know that beta is positive. So we're not so much talking about between minus pi and pi, we're actually talking about 0 and pi. Okay? So from the diagram, actually we can show that beta is between 0 and pi straight away. Because y is greater than 0 and x is less than 2a, beta is between 0 and pi. That's the easy bit. So just once more looking at the diagram, this is beta equals 0 and all the way up to beta equals pi. We're definitely in that range because we know that y is greater than 0 for our p. Okay, that's the easy bit. The tricky bit is proving that alpha, or 2 alpha, is between 0 and pi by 2. So we actually have to show that alpha is between 0 and pi by 4. So we have to show that when we get to this critical point 2a up here, that the angle subtended at r is actually less than 45 degrees. That's our challenge. And it looks true from the graph, but we're going to have to do a bit better than that. So we're going to have to try and convincingly show that that will be true. So let's say sufficient to show that tan of alpha is less than 1 and greater than 0. Okay? And that is because this is essentially equivalent to saying, or no, this implies that alpha will be between 0 and pi by 2, or pi by 4, sorry. And that will be sufficient for us. So, have I put some pi by 2s when it should be pi by 4s? Yeah, sorry. Remember our diagram, the critical point wasn't pi, sorry, it was pi by 2. Let me just put that in. So yeah, beta between 0 and pi by 2, that was the vertical line. And then we need to show that alpha is between 0 and pi by 4. So we need to show that tan alpha is between 0 and 1. Okay, I think that still works. So let's see. Tan alpha, remember, we found was y over x plus a. So that is actually greater than 0 straight away because the numerator is positive, because we're told y is 0. And the denominator is positive because a is greater than 0 and yes, and we're looking at the left-hand branch. So x is greater than 0. We're looking at the right-hand branch of our parabola. So actually, let's say on the right-hand branch. So we're looking at when x is greater than a and less than 2a. Okay, so now we need to show, so sufficient to show now, that tan alpha is less than 1. Okay, so let's work with that. So that's if and only if y over x plus a is less than 1. Okay. So what's the way to do this? Well, we know that y squared, so remember we're assuming that p lies on this curve now, so we know that y squared is 3x squared minus a squared. This is quite nice. We can say from this that y equals the square root of 3 lots of x squared, let's actually factorize that, x plus a and x minus a. And now, if we try and get our tan alpha, let's say y over x plus a, what's that going to give us? It's going to give us 3 lots of x minus a over x plus a, okay, dividing 3 by x plus a. So inside the square root, we're going to be dividing by this squared, which gives us this expression. And so actually, this condition is met. Let's call that star. So star is satisfied if and only if, because we've said that actually this is equal to this, so we can replace this here with this. So if and only if root 3x minus a over x plus a is less than 1. Okay, and hopefully we'll get a condition which we have already assumed. So that's true if and only if root 3x minus a is less than root of x plus a, timesing up by root x plus a. And now that is certainly true if, because we're squaring now, so we can't do the implication both ways, but that is definitely true if 3 lots of x minus a is less than x plus a. And now that's true if and only if 3x minus 3a is less than x plus a. And that is only, that is true exactly when let's see, we've got 4a and 2x, so x is less than 2a, and which it is. We already know that x is less than 2a because we're told it in the question. Okay, so we have shown actually that tan alpha is in the region 0 pi by 4, 0 and 1, which implies that alpha is between 0 and pi by 4. Fantastic. And this shows us that actually tan beta equals tan 2 alpha does in fact imply beta equals 2 alpha. Okay, so on the right hand branch of our parabola, we do actually get this condition on the right hand branch. Where, let's just put in our x value, so that's where x is between a and 2a. Fantastic. Now, let's look back at our diagram. So we've shown that actually when we are along here, the condition does hold in reverse. But what about when we're over here? Okay, so this is when x is less than minus a. So let's try and do a similar thing, but with that, and see what we get. Okay, so this is part 2 continued. And this time we're doing x is less than minus a. Okay, so as before, we've still got our expression for tan x. Tan x equals y over x plus a. But now, straight away, actually, we see this is going to be less than 0. Okay, this is definitely a different case because the numerator is still positive, but x plus a is negative because x is less than minus a. Okay, so let's now try and look for a lower bound for tan x. So as before, we've got that y squared equals, let's say we know y squared equals 3 lots of x squared. Question back for you there. Minus a squared from here. Okay, and now this implies, because we know actually that we're going to have the negative version of this because tan x is negative. Okay, so as before, we have y over x plus a equals, remember we know this is negative now, so we're going to take the negative square root and have what we had before. So x minus a over x plus a. Okay, and now we actually, looking back at our diagram, last time we went up to 2a, but here we don't have any such condition with 2a. We can actually go all the way out in fact to x going towards minus infinity. So we have to look at that now. So as x tends to minus infinity, I'm just looking for essentially, remember this is tan alpha. I'm essentially looking for a lower bound of tan alpha now, but instead of going to 2a, I have to go all the way back to minus infinity. Well, as x tends towards minus infinity, this thing inside the square root, just ignoring the 3 for now, x minus a over x plus a, that's just going to tend to 1, isn't it? Because the a becomes insignificant. Okay? So, for all x less than minus a, we have actually that tan alpha. If you imagine this is decreasing, but it never gets less than minus root 3. So we can actually say that tan alpha is between minus root 3 and 0. Okay, so what does that mean for alpha? Well, when is tan of alpha minus root 3? That is simply at pi by 2. Sorry. Pi by 2 is when it's 0, and when it's minus root 3 will be 2 pi by 3. Okay, and now, well, we don't want alpha so much as 2 alpha. That's the critical thing. So let's just take this up. That means that 2 alpha is going to be between pi and 4 pi by 3, which is not exactly what we wanted, because remember 4 pi by 3 isn't significant in our tan graph. Let's just draw it. So pi by 2 and minus pi by 2. We've got the principal branch here. But actually here we know that 2 alpha is between pi and 4 pi by 3. Let's just look at that. So we've got pi here and 3 pi by 2 here. So we're between pi and 4 pi by 3. Actually, so 4 pi by 3 is actually going to be here somewhere. So actually, yeah, it's enough to show that 2 alpha is in between pi and 3 pi by 2. Okay, so it's enough to show that we're in here, and we definitely are because 4 pi by 3 is somewhere here. Okay, so now let's figure out if we're, let's say, here somewhere, what relation does that have to the principal branch? In other words, when we take an arctan of this tan, what we're going to get? So arctan of tan alpha here, remembering that tan alpha is in here, so 2 alpha is in here. Tan 2 alpha, sorry. What we're going to do, actually, we're going to get something on the value on the principal branch is going to be this, but actually when we arctan the tan of it, when we tan it, the arctan is going to appear on this principal branch, okay? So we're going to actually go pi backwards. Then we're going to end up with this value. So arctan of tan of 2 alpha is just going to be 2 alpha, what we started with, but minus pi. Okay, so we get that beta equals, arctan of tan of 2 alpha. So actually, beta is going to equal 2 alpha minus pi on the left-hand branch, where x is less than minus a. Okay, and that is actually us done. So I would say actually that, at least for me, that was maybe the hardest of the 3 questions so far. Maybe that's just because I'm bad at this sort of question, and I probably didn't explain it that well either. But let's just quickly have a look at the solution. So we started over here, drew our graph, and then we had some fairly easy algebra for part 1 to show that it meets the required condition. But then for part 2, there was quite a lot of thinking required. We had to decide for ourselves that the non-reversible step was the tan beta equals tan 2 alpha into beta equals 2 alpha. Then we had to separate into 2 cases, which we weren't told how to do. And then we had to look at for each case essentially what 2 alpha will be in, what range it will be in, and then find out what corresponding condition on beta and alpha we get. The answer was actually quite simple. Beta equals 2 alpha on the right-hand branch, and then we eventually got that beta equals 2 alpha minus pi on the left-hand branch. There might have been a much quicker way of doing this, because my solution ended up being quite long. But there we go. I hope that was helpful. As you can see, step questions, some of them you'll find easy, some of them you'll find very difficult indeed. But that is question 3 done. Please do let me know if you have any questions, and please do let me know if you have any particular step or other UKMT or something like that, questions that you want me to go through. But yeah, that was that one. I'll see you soon with question 4, and in the meantime, keep enjoying maths, and see you soon. Goodbye.